I think we're good to go. All right, so this is the world's shortest chapter, chapter 4. We'll try to get through it and then on to the next one today, but feel free to derail me at any point because that's how that works. I do want to just say that the first few chapters of this book, as you've been reading them, I'm sure it's just a lot of information all at once. You've probably realized that. I'm sorry about that. It will get better with time. There's a lot of like foundational things we have to build up first before we can do cool like analyses and statistical tests and fun stuff like that. So we got to get through this kind of stuff. I'll do my best to make it fun. All right. So today I want to talk about data types, which are very, very important to us. All right. So this is going to be chapter 4 stuff. So please read chapter 4. It's super short. So we're going in order. All right. So I would like to tell you that there is a type to every piece of data we use in Python. You type a number, or you physically type a number, it has a type associated with it. It has a kind. All right. And let me prove that to you. All right. So let's see. The type, first of all, you got numbers like 42. The type of 42, as far as Python is concerned, that's an int. All right. It's a special kind of number. Int is short for integer. All right. 3.14, if you type that into Python, because it has a decimal place, it's not just an integer. It's not just a whole number as far as Python is concerned. It's like, no, that's a float, which is a weird historical name. It has to do with the word floating point, if you want to look up into that. But the idea is that it has a decimal place, and it can do partial fraction-y things like that. All right? So those are two kinds of number types in Python. But everything you could possibly type, even if it's a variable, kind of depends on what the variable holds. If the variable holds 42, then the type of x right now is an int, an integer. But if it was like 42.0, then it's a float. And then there's more where that came from. We're going to talk about all the different kinds today. All right. So a function technically has a type. It's just the type is function. So let me show those things to you. Okay. If you would like to play around, you're always welcome to go to our, where is it? Our modules page. This Jupyter Lab, just like I want to do something quickly link, will always work for this kind of stuff. All right. So yeah, let me show this to you. It's an interesting fact. You type something in Python, it's like it's keeping track under the hood of what kind of thing you're using right now. So like we learned about numbers. What is the type of 42? Well, 42 you can use it, right? 42 by itself, it is a number, but Python knows what the type of something is with the type function. It's always keeping it deep down in there. So the type of 42 is int. It's like that's a whole number. All right. Remember the round function, like round 3.1415 to like 3 decimal places. Remember that one? Round by itself is the name of a function, and Python knows that. What's the type of round? It's like, oh, that's a built-in function or method. We'll get into those words. So like under the hood, Python is keeping track of what kind of thing this all is. And 42 has no decimal places, so it's an int. Integer means whole number. Type of 42.5, that's a float. It has a decimal place. And so it's stored slightly different in memory if you want to think about that. All right. And the key thing I want to say on this slide, or really in this chapter, is that the type of something dictates what you can do to it. All right. The second you know that you have an int, now you know you can do math. The second you know you have a float, now you can do some math with decimal places. The second you know you have a function, that means you can call it and ask it to do work for you. Stuff like that. All right. So the second you know the type, you kind of have some extra knowledge, don't you? So let's see. For example, 1.5 plus 2. Python plays nicely with both kinds of numbers used together. So it still is like, okay, I'm happy with that. 3.5. But do you see how it kind of up-converted the 2 to like a 2.0? It didn't like lose any decimal places. The result of a float plus an int is another float, because it needed those decimal places, didn't it? That's kind of interesting. Mm-hmm. Yeah, everything has a type. Some things, like operations, give you types just out of the deal. Division in Python. 8 and 2, what are the types of 8 and 2, given what we just said? Can somebody tell me? 8 and 2 have the same type. You say int? Yeah, they're both integers. They're both whole numbers. But if I were to do the division on 8 and 2, no matter what, Python will give me back a float for interesting reasons. So it's like It's up converting it. It's like that's a bigger kind of type. If you want to get into math, like floats are like real numbers, whereas ints are just integers. So that's odd, but cool. And again, if you store something into a variable, that variable now takes on the type of the thing that's being stored. So, all right, if x holds 42, of course you can use x in a larger context, like, hey, what's x times 2 or whatever, 84. But the type of x now is the type of the thing that x holds. So if x is holding on to an int, the type of x itself now is an int. If x changes to something else, like x equals 3.14, then the type of x now holds that new thing. So you can rewrite stuff. You can overwrite boxes inside of Python, which is really weird. You can overwrite types. It's a little disgusting, all right? But that's the thing. So yeah, I think that's what I wanted to say. And remember that you can keep on going further with that. You can do math, okay? Like the type of 8/2 became float, even though both sides were just ints. Odd. Different to other languages. So yeah, any questions about any of that? Just the kind of thing deep down. There's always a name. Yeah.
So regardless of whatever type you start with, it will always like rewrite or whatever. Like if I say print something, that would be like a like that. It would be a different type versus like if I wanted to make a number.
Make what a number?
Like, so it's different like
like words.
Like 11. That would be a string, right?
Yeah, we're gonna get to strings in just a second. Okay. Yeah, don't worry about that. That's a good question. That leads into the next step. So we're going there. Any other thoughts, questions? So yeah, it's a little subtle because in Python you don't really, if you're just doing stuff, doing math and things, you don't really worry about it. Just like it happens for you. But there's always a type deep down of everything. Functions, variables. You got to keep that in the back of your mind sometimes because you might run into trouble with certain operations. All right. Some kinds of types like float, you don't have to make your numbers with just decimal places like this. You could be like, you can do scientific notation. There's a concept of like, we've all seen this, right? It's like 5 times 10 to the 6th power, like that kind of notation, right? You can do that in Python by saying 5e to the 6. E is just like exponent, I guess, kind of. Take 5 times 10 to the 6, you can say 5e6 in Python, and it will understand that. So there's some shorthand for like, that's a float kind of type. So it's got the 0.0, you see it. And so, yeah, sometimes if you want to type that kind of stuff, there is shorthand depending on the types you're using. I do want to say, though, that the float type, while we're on it, is an imprecise type. You only get like 16 decimal places of precision in scientific notation land with floats. And so let me show that to you. If I take this number, I don't know, a bunch of 5s. Let me give it 16 digits of 5s. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And I don't know, I subtract from that the same number. And then I start adding stuff. 5, 6, 7, 8, 9. This should be a negative number now, right? No, it's 0. So that's another odd thing. So there's a concept of floats being only so precise. Floats are not perfectly precise. You only get 16 decimal places, about 16, because it's stored in binary, 1s and 0s, if you've heard of that. We won't talk about that in this class, but that's kind of why. You only get about 16 decimal places of precision, we say. Any more than that just kind of gets thrown away. And so usually 16 decimal places in scientific notation is good enough for all of our worldly purposes, but you never know. Now you know. Okay? Any questions about any of that? So like types. They tell you what you can do, and they tell you what to expect as well. Got to keep it in the back of your mind. Yeah, what else do we know? Yeah, another example of like floats doing weird, imprecise stuff. You know that the star means to the power of, so 2 to the 1/2 power means the square root of 2, right? And so we get that answer, which is more or less precise, up to 16 decimal places. But what if I were to do this? The square root of 2 times the square root of 2. What should the answer be? It's like 2 to the 1/2 times 2 to the 1/2. So like you add the 1/2, so it should just be 2 to the 1, yeah? 2. No, it's a little bit bigger than 2. So there's some imprecision going on at the end there. And as long as you use like the round function, like that's fine. It'll all work out at the end. But that is something to potentially worry about one day if you're doing very precise math. Maybe you want to use a library that makes it so that this doesn't happen. All right, but floats by themselves, a little weird. Okay, so those are those 2 types, number types, ints and floats. Ints are perfectly precise. You can't get into weird trouble with integers, but floats, you only get a little bit of precision, 16 decimal places of precision. All right, so you gotta be careful. Yeah, the other like main kind of type that we care a whole lot about is like words. We're storing text a lot of the time to print stuff later, or just like to add into our pretty graphs and things. And the type of words, stuff between quotes, either single or double quotes as far as Python cares, those are called strs. It is short for the word string. So you can think of them as like strings of characters on like a friendship bracelet or something. But str is short for string, and that's just the type that means text in Python. So anything between quotes, we ask the type of that. It's called a str. So that just means text. It's shorthand for the word string, which is what we use in computer science to say like just a bunch of text. And Python does not care if you use single quotes or double quotes, as long as you're consistent, like you end one with the other. Like type, what is the type of hello world, which is like a standard thing that we use a lot. Again, it's a str, all right? And so by having a str, you can do things to it, all right? It is now possible to like do text-based operations. If I have a str, I can't really do math, right? Math things are happening up here. Text things are happening in str. So let me show you that there is a way to do like math in, or not math, sorry, but like the addition operator still works on strs. Let me show that to you. So we got, dun, dun, dun. Going to my example. So let's say I've got the word data, and then I've got the string also space 8. I can add 2 strs. Doesn't even matter if I was consistent with the parentheses around the 2. But the plus operation, when it sees 2 strings, 2 strs on both sides, it works differently to numbers. It's like, all right, that will build up a new str, data space 8. Does that make sense? So that's kind of cool. Just like the fact that the types were different, that's how Python knew. It's like, all right, I'm not going to do math on the word data and the text space 8. It's like, I'm going to produce a third str, kind of, all right? And because you have options with those different kinds of operators in parentheses and quotes and things, sometimes you want to use the double quotes versus the single quotes. Let me show that too. Like, can't do this with single quotes, can you? Because if I were to try to write this exact str with single quotes, can't do this. Do you see how it changed colors with stars? It's going to get very concerned about this T right here because it thought that the str was over right there. You see it? So there's ways to get around this, but it's kind of interesting. The answer is to use like a backslash. I don't know if I want to show that to you today though, but you have options, I guess is what I want to say. So let's see. Yeah, I want to motivate the next slide in just a second. So, all right, let's say you're building up an answer, like you're making a fancy program to calculate a cool number or something. You want to print out the answer. So you want to say something like, the answer is, or my calculation is, blah, blah, blah. And then you want to add in your answer. This won't work. I'm going to get, it's called a type error. So luckily it's kind of helpful, but what I'm trying to do here is add a str text to this result, 2 plus 2 in Python. That's the integer 2 plus the integer 2, so the integer 4. So I'm trying to add a str to an int, and it's like, I don't know what you're talking about, dude. That's what it's saying right there. So if I want this to be part of my output, like I want to turn kind of the 4 into text. Does that make sense? That's what I would like. I don't want this 4. I would rather have this for? Because that one I can put inside of that stir, yeah, and add to it. So there's a huge, huge difference between this one, and it's even color coded, isn't it? So now we have to talk about converting types. All right, so you're allowed to convert one type to another. You can ask for, hey, Python, I know I have this int right now. You can call the type that you want like a function, which is really nice. You can say, hey, Python, I have this right now. I'd really like it to be a stir. Can you do that for me? And this will get turned in. It will result in the stir 42. All right, I'll use double quotes just because you can be interchangeable. And you can go the other way. If you got like the user's input, like you get text from the user somehow, you ask them to type stuff in, you're getting that in text form. So if you had the stir 42, just like the digit 4, then the digit 2, it's not a number yet, you can ask the int type, use it like a function to say, hey, this is just text right now. It's not the same. It has no meaning yet as numbers, but I promise it's a number, Python. Can you please convert it to the kind of number I want it to be? So like if you know it's a whole number, you can give that stir and it will produce 42 without any quotes. Does that make a little bit of sense? That's how that'll work. And then you can always like ask for like an int, right? An int is not a float, but you can ask it to become a float and this will produce like 1.0 for you. You can ask that type to turn it into it, all right? So the moral of the story is the way to make this work now is to say, okay, take like 2 plus 2, that answer that we wanted, and turn it into a stir. And this is a good example of how function calls work as well, because like it needs to turn whatever this becomes into a stir. So it does the math first. It produces the int 4 and then turns it into quotes for the stir. And now you can add it into your larger place that you wanted to use it, stir. And now it's happy. And that's what you could print out to the user. You can print it on your receipt or whatever, if this is like a checkout stand program, whatever it needs to be. Okay? Any questions about that? It's a little subtle. It's like the types are very important here. And I guess a way to drive that home is like, what if I had these two stirs, 42, 42, and I added them together? What do you think I'll get? Will I get 84? I'll get something else, right? You kind of see it? I'll get the stir 4242 because as far as Python is concerned, anything between quotes is just text. It's like the digit 4, the digit 2, and the plus on stir is just like adds those characters in order. It has no concept of number stuff. But you can ask it, hey, no, I had these stirs for some reason. I really wanted them to be ints. You can ask them to be turned into ints. Python knows how to do that. This is definitely contrived because you just type 42, but it's a good example. And so this will now produce the number 42. So now produce the number 42. Now this is the plus on ints, yeah? And now it will give me the normal 84 that I want and I would like to have, okay? Any questions about any of that? I don't know if that makes a little bit of sense. Converting types. I have some weird questions for you now, all right? So please go to the ByClicker page and humor me. I'll give you a few minutes to try these out with the people sitting next to you. Convince your neighbors that you're correct. So try to think about all of these, and I'll just like rapid fire after a few minutes. We'll come back and we'll talk about all of them. But these are some odd ideas, because they maybe don't make a whole lot of sense. What do you think is going to happen? You can try it if you'd like, but in your mind first, please think about this. What do you think is going to happen if we were to do these things? What do you think the Python developers were like? This is my thought here. This is what is going to happen. Do you think that if I said int of 2.5, am I going to get an error message in just one word? Is it going to not be an error message and like do what I expect? Or is it going to be not an error message, but I'm not going to get anything that I expect? All right, not an error, but the answer still makes sense. Does that make sense? The question. So think about all of those. If you want to cheat and try them, do it after you thought about it, all right? And then we'll enter in our answers real quick after a few minutes, but I'd like you guys to get into little peer instruction groups, discuss, see what you think, and we will come back in a few minutes.
We're only number 1, right?
Oh, I want you to discuss all of them, but you can enter in your answer for number 1 if you'd like. These should make you feel uneasy, these thoughts, right?
like it's.
As you're pondering, let me try and explain why these are all weird. So 8 to 2.5, trying to make a whole number, right? Something like that. And then for the last one, hello's already a stir. What's going to happen? Maybe that should be an and not a but. And the answers.
Yeah.
All right, our words are dying down. Are we ready to enter in our answers? So get in your answer for one. What do you think? Morally, what should happen here? And then we'll do the rest after we talk about that. But this one's weird because, like, ints don't have decimal places, do they? It's like, what's going to happen? That's the question. Will it let it happen? Let's see. Look at us. So B or C, we don't think it'll give us an error, which is nice, interesting, because it's already a kind of a number, right? 2.5 is a float, right? It has decimal places. Ints don't have decimal places. And so if we think it's not going to give us an error, I guess our two options that make sense in our minds are like, all right, either it's going to make this thing, it's going to round it up to 3, or it's going to, like, I guess 2 is also an option, right? Well, let's see what's going to happen here. Int 2.5. It doesn't round it. That's a little surprising. I would say that would be maybe C. We've never seen that idea before. So why? Why does it do that? Well, I guess it's less thought. It's less work for Python to just like, all right, there was a decimal place. I'm just gonna chop everything after that off. Just like calling it a day. It's less computational effort, I guess. But yeah, if you try to convert a float into an int, you're losing information and it does not get rounded. All right, we're gonna remember that. I hope it's a very interesting idea. And then, all right, what about 2? What's going to happen to this one? Give you a few seconds to enter in what you thought for that one. Like, all right, if I type out 42, does Python know what that meant? Like the stir 40-2, converting that to a float, of course. Does that really give me back? We'd really like, right? 42.0, I guess. Do I get it? Let's take a look. Nice. We all found that that's probably an error. It cannot keep track of all the words that mean something. I guess technically your other option is like, if this wasn't an error, what would be some value that it would give back? Maybe like 0 or something. Something that's like, all right, I saw no numbers, so like my default answer is 0, but it will be an error. Good. It's like, all right, we found that. Okay, float of 42. It's like, I don't know what you're saying here. It found no digits, I guess. So that's what it's complaining about. So good. We noticed that. And then what about 3? 3 doesn't make us feel super uneasy, but it's still a little odd, right? If you already had a string What would stir do to it? What do we think? What could be our options? Like, all right, one could be errors, like, why would you try this, dude? How dare you? Question mark. It could like make a stir with extra quotes in it. You keep it the same. Who knows? What do we think? What do we find? Nice. So we're thinking B, and yeah, it's not going to be an error. It's just, it's a silly thing to do, I guess, but it's still going to work out. If you have something that's already a stir, or have something that's already an int, and type an int in there. It's like, my job is done. I have to do nothing at all. I'll just give you back the thing you gave me. That's what happens. So yeah, I hope these ideas make a little bit of sense. Are there any questions about any of those? A little odd. But now we've seen them and we will remember. What else do I want to do? Here are some operations, I guess. I want to show you some operations on things that you could do. So, if you have stirs, like data 8, all lowercase, there are some operations. Remember, like for tables, I was using the dot and saying like, hey, table dot select some of the columns, stuff like that. So it's like we're talking to the thing, like asking the table to do something for us when you use a dot like that. So data 8, like the stirs also have some operations that you can ask to have happen on that stir. So you use a dot for that. Like, hey, data 8 dot convert yourself to uppercase. There's also a lower, but that will like produce a new stir that has like had some effect happen on it. And so you can search for the kinds of things that you can do to stirs in Python. It's not just plus, okay? So there's that. There's also a replace that might be useful one day. Here's a fun example I stole from the book. You take hitchhiker, and you say dot replace. Replace takes two things. It's like what you want to replace, and then also what you want it to replace, to be replaced with. You can replace hi with ma, and it turns it into matchmaker. So it's going to replace every time it sees hi with ma. So those are some ideas. And so there's ways to like, if you're going to be a data scientist one day, it's like you're getting a bunch of text out of a database probably, and you're probably going to want to mess with it in some way. So like stir operations are things to want to learn. Okay. So that I think is all that I want to say about stirs. Are we ready for comparisons? That's another thing that we'll really care about in this class. All right, that's the last piece of this slide. So a comparison is when you ask a question in Python, and we want to ask questions all day long, like, all right, is chocolate good to eat or something? I don't know. We're going to do some statistical tests eventually. And so we want some yes-no answers in Python. As far as Python cares, we don't use the word yes and we don't use the word no to mean yes and no. This is like a computer science thing. We say true or false instead of yes and no in Python. All right. So you can ask it stuff. You can make comparisons. You can compare one thing to another and ask Python, hey, what's the result? Is 2 less than 3, for example? That's a comparison. And it will do the work. It will ask itself and see that, oh yeah, 2 is less than 3. Yes. Yes, it is. So true means yes. All right. So that's what that means. 3 less than 2. No is false. So it's going to ask itself that you're asking that question to Python and it says, no, 3 is not less than 2. False. It's not true. Okay. So yeah, just get used to the words true and false. Those are going to appear a whole lot. And there's a whole bunch of comparisons. Less than, greater than. It's hard to type like the less than or equal sign. So like you just do it less than, then equal. So that becomes that inside of Python. So it's like, hey, is 2 less than or equal to 2? Yes, that's true. This one's not true. So this is a good slide to look at later, potentially. If you want to check if something's not equal, like this kind of sign, hey, is 3 not equal to 2? The answer is yes, and you use an exclamation point to like mean that. Like read that as the not part. So that's interesting. Is 2 not equal to 2? No. So that's a false answer, isn't it? And then to check for equality, like, hey, is one thing equal to another? In math, it's the normal single equal sign. But we've already used the single equal sign in Python, haven't we? X equals 42. This is not a comparison, is it? That's called an assignment statement. It puts something into a variable. And so we have to have a different equality check operation. Because we're going to do assignment to variables more often than we're checking for equality. And so we're going to use 2 equal signs to ask if something's actually equal to something else. Like, hey, is 3 equal to 3? Yes, true. Is 3 equal to 2? Double equals. No, false. All right, so you gotta watch out for that. Python will complain if you do it, at least if there's no variables on the left. It's like, I cannot do this. Maybe you wanted double equals instead of single equals. Yes, we did. Is 4 equal to 4? Double equals. True. Is 2 not equal to 3? You read that exclamation point as not. Yeah, it's not equal. I think that's more or less what I wanted to say. Python's kind of cool because you can do kind of the math chain of inequalities. Like you've seen this kind of stuff before, like, hey, is 2 between 1 and 3 is kind of that question, if you've seen that in math before. And it'll just make sure that all of those things hold, which is kind of neat. It's like, yeah, that's true. Can't do that in a lot of different languages. So yeah, there's a bunch of comparisons that you can make. And let's see here. I think that's most of what I wanted to say. There are some different types that you can compare. Like numbers, of course, you can compare. But you can still compare strs. Is high equal to high? Absolutely, right? You can also compare for inequality. Is high less than mom? And that is actually true. And the way that strs are compared in Python is dictionary order. It's like high came before mom in the dictionary. That's why I did it that way. You do run into trouble with capitals, though. But the type of answers, type of comparisons, yes, no answers, like what's the type of true? It's called bool. It's short for Boolean. It's a man's last name who invented this kind of math that you could ask questions and say yes or no with. But yeah, I think that's more or less what I wanted to say on those slides about comparisons. Any questions about those? It's like you can ask questions and get an answer back. All right. So yeah, now is the time for random things that you'll need in a lab one day that I want to talk about from this chapter. So my favorite section, miscellaneous things Lottie needs to teach you. So this is not as exciting, or maybe it's more exciting, but it's not as important as those things, but it's still cool. So remember the math library, import math. You can start using stuff like math.square root 2, math.pow, stuff like that. There's also variables defined in the math library, like math.e, math.pi. So it's not just functions, which is kind of cool. So you don't have to type pi out. It's like part of the math library. There's that. In addition to rounding, which is just built in, like round 3.1415 to 2 decimal places, there's also cut stuff off functions in the math library. There's math called math.floor. That's one operation. We had e. This is a weird one. What math.floor does is it takes a float and it pushes it down to the floor, kind of. It's getting rid of any decimal places by bringing it down to the next smaller integer. So that's going to be brought down to 2. Does that make sense? Being pushed down. If it's already a whole number, it's already 2. It's staying 2. It's just like getting down to the closest one smaller than it or equal to it. All right? It's like you're pushing it down to the floor. Question?
Is that the exact same as int? Like, can you use them interchangeably?
Like the result?
Yeah.
The result of floor, like, is this your question? What is the type of the result of a floor operation? It is going to be an int.
No, I found instead of using floor,
Oh, yeah. Yes. Asking for the integer version of something is equivalent to using floor. Yes. Good. Questions about that? Does that make sense? That is exactly the same. I wonder how they implemented it. Maybe they did use, just converted it to an int like that. So that's an interesting idea. And then the flip side of floor is ceil, math.ceil. It like pushes the number up to the ceiling. Give me the next one that's equal to it or bigger. So that's a little bit of the opposite. Cool. So there's that one. And I have a question for you to ponder now that you know what that does. The round, if you want to round a number to the nearest whole number, you can use math.floor to do it. Remember that math.floor brings it down. So math.floor on like 2.7 gives you back just 2. Can you fill in this blank? So like, if you had a number x, like whatever it was, could you fill in this blank to round x to the nearest whole number? Can you think about that for a minute? It's kind of interesting. Like if x was 2.7, what would you put here to make it somehow 3? This may be how the round function is implemented. So you don't have to write it down. I just want you to think about it for a second, and I'll give you the answer. It's a really cool fact. What was I going to do here? It's an interesting idea. Oh, don't make noise. Okay, good. This, whatever we put here has to work, right, for anything. Like whatever number I put here should work for anything to round it. So like if x was, I don't know, 2.5, whatever I put here should somehow make it at least 3, right? If it was 2 point, let's think about our range, right? If x was 2.4, then whatever I put here should still be brought down to 2, right? And then if x was 2.5, suddenly now it's made it above. And then anything bigger as well, 2.6 and on. So that's kind of the range of things that could have been an x. Does that kind of show you the answer? If it was 2.4, and I added something to 2.4 and it stayed 2, that means it was still 2 point something, right? If that's the secret. But 2.5 now, if I took the floor of something 2.5 and it's supposed to be 3, then it should have become at least 3 point something. Does that give any hints? Yeah. No, it's 0.5. It's the number 0.5. Just think about it. If you took 2.4 and you added 0.5 to it, now you got 2.9. And then if you did the floor on that, you brought it down. That's the mathematical way to mean floor. Then it's still 2. But if it was 2.5, you added 0.5 to that. Now it's 3.0, and you did the floor on that, but it's already a whole number, so it stays 3.
You just add, like, you're supposed to say it was 2.4, you just add 0.6, or just 0.5, like, top of it?
Well, this is like the implementation for anybody. Like this code should round any x. That's what I'm trying to say. Does that make sense? Yeah. So that's one way that could be implemented, which is kind of cool to think about. But yeah, now you know. So these are just math operations. You can search Python math, Python stir to see more cool things that you can do. Let's see. I guess before we go, let me show you, before I do other things. Let's talk about this one. Remember this idea. I can't do this. This is an error because I put an apostrophe here, but it thought it was the end of the string. I could do it with double quotes. I could fix that. But a way to keep the single quotes and make it work is to what's called escape that single quote. Like put can't here. And this is meant to be an actual character in stir. It's not supposed to be the marker for the end of the stir. If you put a backslash, like these two together become the single quote character. So that's the way to get around that, if you care. One day you might need it. So there's that. And then the very last miscellaneous thing for this chapter is that there's a len function. If you ask for the length, for the len of a string, of a stir, it tells you how many characters were in it. So that's a useful idea. Like how big was, how many characters were in this book that we just read into a variable name. We used len on that for like the first day's example kind of things. Yeah, I think that's what I wanted to say about chapter 4. We got types, and we got a bunch of things that we can do to those types, and the types dictate what we can do. Like adding stir to stir is completely different from adding int to int. Yeah, that's what I wanted to say. Any questions? Yeah.
Are there like inside ints or more?
Oh, Python. Yeah, this is a question for those of you who have not taken a CSci 40 kind of class yet. There are different, in other programming languages, there are ideas of like, we can hold only so many digits in our ints kind of deals. In Python, you can hold as many digits as you want. Python does not care. It will make the biggest int that it needs to make and use as much memory as it needs to, which is great news for us programmers. Yeah. Any other questions? So that's wonderful. Yeah, so that's chapter 4. Not too horrible. And then make sure to do attendance. I'll stop that eventually one day. I would like to start chapter 5. Why not? We may be able to get through it. We'll see. It's another shorter chapter. I want to talk about a bunch of data all at once because that's what we're going to deal with as data scientists, right? I want to talk about sequences and representing the idea of like not just one int, but like 50 ints, 5,000 ints. So yeah, let's go there, and this will be chapter 5 stuff. Right? Again, a shorter chapter. The first chapters are pretty short. So eventually we will stay on a chapter for days, but for now at the start it's not like that. If you would like to play along with this stuff, again you can click whatever I do today right now. Again, you can click this link. You can say go here and click this. But that first thing at the start is going to be important because we do need to import some libraries, those default ones. So you can just keep that going there if you would like to play along some more there. So make sure to run that first cell that's already in that file. So yeah, I want to talk now about the idea of an array. That's the word of the day. So an array is Python's concept of a sequence. It's a kind of type, again a type, that holds little baby types inside of it. It holds sequences of values. All right? It's a type that holds other types. So a sequence kind of looks like this. Instead of just 142, we can put like 42, then 43, then 44, then 45. It doesn't have to be in order. We could have -1 after that. It doesn't matter. But there's a concept of a sequence of things, and there's an order to those. Okay? And you can put all of these all at once into like a variable x, or variable a to mean it's an array or something like that. So it's representing the idea of like with one name, a bunch of numbers at once, which is nice, right? So an array is a type that holds other types, kind of like this is an array of integers. That could be a thing. You can have an array of strs, and arrays come from a fancy library that we care a whole lot about in this class. It's called the NumPy library. It's like does numerical things, one of which is hold a bunch of stuff at once, and it gives us some cool operations on like arrays that we'll care about, especially if we ever get to be like machine learning scientists like this. You can make some cool stuff with the NumPy library. I'll show you a little bit of it in this class. All right, and I'll eventually show you what this means. Okay, so not a ton of slides today, just a bunch of examples. So, okay. If we want to do stuff, eventually we're going to need this NumPy library. We get a piece of it when we include our data science library. So if we say import data science, which is kind of what I did at the start of this, it's like from data science import star, that's really what we want, like into the top level. From data science, give me everything. We get a bunch of stuff. One thing that we get is a function called make_array. That's what we care about right now. You can make an array of like 42, 43, 44, and that will give us back an array of things. And it is trying so hard to run these right now for me. I may have to tell it to hurry up. But that's how you build a sequence at least in this class. You give it to the makeArray function, you give a bunch of things, as many arguments as you want to build up, and it puts all those into one place, a sequence called an array. Okay? And why is it taking so long to do this? I have no idea. Sometimes, if it's like unhappy, you can say restart kernel. Just tell it to try again. Like gets rid of all the memory and tells it to do things all over from scratch. So I guess while we're waiting on that, there's other things that you can put into arrays. You can be like make array of strings and be like, I'll do Pokemon because why not? Pikachu, Charizard. Doesn't have to be single quotes either. Squirtle. So let's say that that's my array that I care about, and you could save that into a name. You can be like, that's the array of Pokemon that I like, and then you can use that. All right. So again, why is this not working? I will never know. I think I might just have to restart the program. It worked for the last one, and then I got really unhappy, it sounds like. That's no fun. And it says that it's idle as well. Yeah, I'm just going to restart this. Worst case scenario, I go back to this website. Dun, dun, dun. That one. You can do it, little Python. I guess I can show it to you on the website while that's thinking. So here, because this one, we can run this one right there, and it should be happy enough. Yay! So it's like make array of 1, 2, 3. That's what this looks like. It's like, all right, gives you back an array. It's like, sure, yes. You can ask for the type of that, type of the result of make array. Like, what is the type of it? It's like the NumPy array. It lives in there somewhere secretly. So that's the thing. I am so confused why this is not happy right now. I don't like that. So there's that. What else? Yeah, I guess I'll work on here. I'll try to save it, I guess. Let me copy paste all this. Like Pokemon I like. Is this kind of array? And you can ask for like, okay. It's saved as a variable, and you can always get it back. Use tab to autocomplete. Like, okay, now it's an array of stirs, of words. It's happy like that. Remember the len function that told you like the length of a string? That still understands like arrays. Arrays, you can ask how long they are. That's so weird, man. Restart, reconnect even. Kernel status unknown. Idle. I don't get it. Maybe I just have to restart my computer. It's been on too long, but I'll work here today. So yeah, you got that one. You've got, let's see. I guess I just want to stay here then. You can ask for the length of it. What's the length of the Pokemon that I like array? 3. There's 3 things in it, but each individual thing, like, they also have their own lens because they're stirs, right? That's interesting. So there's that. You can also ask for pieces of those arrays, all right? So those are things that you could do. Again, restart kernel. Just gonna keep trying it until it's happy. It's like it ran it. It says that it ran it, but it doesn't understand that it ran it. That's so weird. Try again. Well, maybe Jupyter Lab was not the best one to recommend for the class. Sorry about that. Have you guys experienced problems like this while you're trying your labs? Could just be my computer. I'm gonna let it think about just that first line for a second. I really don't understand. So yeah, you can ask for the length of an array. You could also, still going. You can also get pieces of it. Because like if this is an array, like I've got 3 things in it right now. I have this thing, and this thing. If I want the first thing, like what was the first thing of that array? Because I've called it like all at once. If you say its name, you're getting the whole thing. You're getting every piece of it. If you would like just the first thing, you can ask for that. You say the name of the array, and you ask it to go to .item, and then there's what's called an index. Then you put what index of thing into the array you care about, and I get to teach you now that arrays start at 0, all right? So if this was my sequence, if this was my array, 8, 6, 7, 5, 3, if I wanted the 8 out, I would go to .item 0. That's what you would do. Like if this was called A, then you'd say, if I wanted the 8, I'd say A.item 0. So the first thing is the 0th thing in pretty much every programming language, except for the language R, which I may teach you at the end of this semester. So that's the odd man out. It really is. Every other language that you could ever probably learn, 0. The index 0 means the first thing in a sequence of things. So if I wanted the second thing, it's really index 1. So A.item 0, that would give me back 8. If the thing's name was A at least. A.item 1 would give back the 6. Weird to think about, okay? So if I want Pikachu out, that means it's item 0. Does that make sense? It's odd, but we'll get used to it. If I want the second thing, it's item 1. Item at index 1. Very easy. Hey, it finished. Nice. Yay, let me copy and paste everything because like it's saved there for sure. Let me save every single thing. We did this one. Can I just like copy a bunch of cells at once? Probably not, but just so that you have it, I want to make sure. Dun, dun, dun. you have all these pieces. We got that one. We asked for the length. Just do it really quickly. The length of that array is there's 3 things in it. If I want the first thing, that's item 0. If I want the second thing now, that's item 1. Cool. All right, I'm happy. Who knows what happened to this file, man? But at least it's good now. Cool. All indices, yeah, they start at 0. So the last index is an interesting one. There's a way to calculate it with the len. If the len of this array, that's 5 things, right? You can always get at the last index by starting with the len and subtracting 1. That's a way to get to the end, if you ever need that. I'm going to go backwards. So there's ways to do that. And I think, yeah, I just want to show you some cool array stuff, because like this NumPy library arrays, they're very cool, overpowered. You can do some very cool math. So let me show that to you. We got, for example, let me make an array of numbers. So make array, and I would like 100, 78, 32, negative 40. And let's pretend that these are like temperatures in Fahrenheit. I'll show you where I'm going with this is I would like to convert them to Celsius. All right. So if I have an array, here's a cool thing that you can do. You can multiply it by something. If you multiply the array by 2, it goes into every piece and it builds you a new array with all of those numbers multiplied by 2. That's kind of cool. You can ask for, instead of len of your array, you can also ask it for its size. Temps f, it's like there's a variable inside of it. It's not a function, it's just a variable inside of it secretly. Hey, temps f, what is the size of you? It knows. It's like, I got 4 things. You can ask it to, like, these are all things that you can do to NumPy arrays. Temps f dot, you can ask it to sum itself. It takes no arguments, it's like it's acting on itself. Which is cool. Like, all right, the sum of all these numbers right here is apparently 170. There's more where that came from. You can ask for it to like give me the average. Another word for average in statistics is mean. Give me the mean of all the numbers in that sequence. So we're going to care a whole lot about these kinds of operations as we get to like statistical things. Okay, so the backbone of this class is going to be sequences, a lot of it. Okay, because we're just given a bunch of data that are going to be in a sequence form. So yeah, let me show you some other things that you can do. I also put this link here, this Python reference. This will be useful for the class. I've also linked to this in other slides already. Like, here's a bunch of stuff we can do on tables. And if you scroll down, here's a bunch of things. String stuff, cool. Just built-in things. And then array stuff. You can ask for the maximum, the minimum, the sum. You can ask for it, the mean, the average, stuff like this. But if you now import the NumPy library, which we're about to do, you can get access to these, like NumPy dot, like, give me the average of things. So there's another way to do it. All right, give me the standard deviation if you've heard of that. We'll use diff in just a second. Give me the square root of every piece of that array. It's like you'll come to this a whole lot in this class. Like, these are things you can do to arrays. So I encourage you to look there. But you know, let's see, where am I going with this? One cool one is you gotta import the NumPy library if you want to do fancier things with the arrays. And everybody, all the cool kids, they don't just say import NumPy, because then if you were to do that, everything that you could ever want to do would be like numpy.blah, and that's a lot of typing. So you can import NumPy. Everybody does it like this. They say import NumPy as np for short. And then once you do that, now you can say, instead of numpy.everything, you say np.everything, because it's always the name first. So now we'll say np dot like diff. So if this is our sequence, 178, 32, negative 40, if you say np dot diff, that sequence, what that does is it computes the differences. It computes another sequence of the differences of the pieces. So like if 178, what's the difference between them? It's going to do the second minus the first, like 78 minus 22. What's the difference between those two elements? 22, and then it'll scoot over. It's like, all right, 78 and 32, what's the difference? What's 32 minus 78 now? Negative 46. And then what's negative 40 minus 32? That's a very small number. Like, what's the difference between those? And like give you the differences between the pieces next to each other. So sometimes we care about that. Like, how much did it change from the next reading. Like if this was like a reading of some sort of like, I don't know, some farming equipment. Like what was the temperature difference between now, an hour ago, 2 hours ago, stuff like that. Like how much did it go up after an hour? That's what diff would tell you. It's like it's taking the little pieces. Give me the difference between those, difference between those, difference between those, and it'll give you a sequence that's one smaller than the original sequence. And yeah, that's just something you may need one day. Now let's convert these temperatures with these kinds of things to Celsius. All right, so here's how you convert to Celsius. You take your temperatures in Fahrenheit. You subtract 32 from them. Okay, and then you multiply by the special constant that takes Fahrenheit to Celsius after that. It's 5/9, I believe. So that's your new array. And so checks out because 32 becomes 0, and -40 is the special negative temperature that is the same in Celsius and Fahrenheit, because they are just two lines. They cross right there. And then 100, apparently, 100 degrees in Celsius is 38-ish Fahrenheit. So 138, or sorry, 100 degrees Fahrenheit is about 38 degrees Celsius. So this could be like temps. See, and it computes a new array. So there's that one. Is happy. Are there any questions about any of this? Just like sequences and stuff you can do to them. It's like a bunch of examples of things that you will be forced to use in a lab. Yeah, that's what I wanted to say about those. And again, there's a whole lot of these kinds of things. NP dot, blah, blah, blah. NP dot stuff. So if I've got all these numbers and I want to like give them to the user, if I want to give them to like, if I want to print them out to show my boss or something, they're a little ugly looking because they're all like a bunch of repeated decimal places. You can say np.round, take that array of all these temperatures and just round it to 2 decimal places. And so that's like, this is a better thing to give to somebody, I would say. That's better looking. Yeah, that's sequences kind of in a nutshell. I just have a bunch of examples after this. Does it make enough sense? Just a bunch of numbers in an order. You can get at each piece if you need to with the dot item, stuff like that. All right. Let's see. What do I want to do next? I just want to show you the kind of stuff that you can do. Before we get there, we're going to need this one day. True means yes, right? It's like, is 2 less than 3? The answer is true. But you can also add true and false. It's a little disgusting. So true, as far as Python and a lot of languages actually are concerned, true means 1. Like, also like yes, no, on, off kind of. True means 1, 0. True means 1 and false means 0. So if I were to do true plus false plus true, the answer is going to be 2, which is disgusting. But now we know, all right? And so there is a special NumPy function that is going to make use of this one day. Let's make an array of yes-no answers. Hey, is 1 less than 2? Is 2 less than 1? Is 8 less than 7? Is 42 less than 43? So it's being represented, first of all, the trues and falses are being represented into 1s and 0s. That's what happens in array land. So that's yes means 1, no or false means 0. And you can ask NumPy how many things were true by asking it how many things were non-zero. Count underscore non-zero on your array. There were 2 things that were non-zero. And so this is like a 2-step process. You make an array of comparisons, which is weird. You get yes and no answers, and then you ask it how many of those were true. This is going to be a key piece of us doing statistics in Python one day, all right? That's why I'm showing it to you now. It's a very weird thing to want to do, though, all right? So there's that. If you have an array of words, array of stirs, my Pokemon array, you can ask it. There's like NumPy character stuff, mp.char. Convert everything to uppercase and give it the array. It's like a fancy function. It's like within the character stuff, do the upper function on everybody. And so it's now capital Pikachu, capital Charizard. Interesting to think about. All right, we're good with that. It's just things, you don't have to memorize any of this. You can come back to this page, etc., etc. All right. So I'm gonna let you have a cheat sheet on all your tests, for example. It's just stuff that you, at least I will have shown you once, kind of, all right? There are ways to now build a sequence, and that's what I really care about showing you now. This is like the last thing that's important. And then there's just more examples. If you say, is it here? It's np.arange. The A is short for array. Make an array from a range. So if I say np.arange and give it 5, this is a way to generate a sequence. It will generate all of the numbers. It starts at 0 by default, and it goes up to, but not including the number you gave, up to 5. So it's a sequence of 5 things, 0 through 4. So np.arange 100 would be 0 through 99, stuff like that. That's a way to generate a sequence, and you can get very precise. You can say, these take a bunch of optional arguments. So np.a, give me an array range from 10 to 20. So you can give a starting value, but still the ending value is always required, but it just never goes up to that one. It's always strictly less than that one. It's like, all right, start here, go up by 1 to get to 19. So it's still 1, 2, 3. There's still 10 things in it, right? But it's just like 10 to 19. Does that make enough sense? This is a way to generate a range of numbers. Like if I want 1 to 100 right now, do you kind of see what you would do? And np.arange, what could I put to go from 1 to 100 given this pattern? What are our thoughts? I want this, like 1, 2, all the way to 100.
Or 1, 2, 1.
Any other thoughts? Well, yours was 1 to 1 to what?
101.
1, 101. Do we have any other thoughts? Do we agree? Disagree? If I want all those numbers, the first one, the second one, let's see. Yeah, that'll work. So the first one's inclusive, the second one is exclusive. I guess that's the wording. That's a way to do it. Let's see. So that's a good one. What else? Let's do np.arange. There's one last thing you can do. By default, it counts up by 1. If you do not want that, you can do it this way. Please give me the numbers from 5 to 100. So I'll go to 101 instead, right? Just to make sure we get there. Counting by 5s. There's a secret third thing that you can give now. So it's always start, end, offset. How much are we counting up by? So does everybody see why this is going to start at 5, increment, like go to 101, but not exactly 101, but increment by 5 each time. So that's how you build a sequence. Like you'll get used to using this. You'll use it so often in this class, but that's a way to count by a certain number. And you can go in reverse as well. You can definitely go in reverse as well. So if you want, like, I would like to go from like 13 to 12 backwards. So I'll show what to put there. Backwards by like negative 0.1. So like I want 13, I want negative 12.9, or 13, 12.9, 12.8, 12.7. I want to go all the way to 12. So I don't put 12.0 here. I'll put 11.9 because I just want to not get to that one. Right? It's always exclusive of the last one, even if it's going down. So this is a way to generate a decreasing sequence if you give a negative offset at the end there. So that's how it builds the next one. And it's always going until it hits this one, and then it stops. All right, it does not include that one once it gets there. Okay, I think that's what I wanted to say. Yeah, any questions about building ranges like that? Because you can do some really cool stuff with ranges, and I might as well show that to you now. One cool example, at least, of the day. There are a bunch of different ways to calculate pi. Here's one way. If you take pi is this infinite series sum. If you take all this stuff, apparently this is a way to calculate pi over 4. If you do this to infinity, 1 minus 1/3 plus 1/5 minus 1/7. So like it goes positive and negative each round. So that's kind of interesting to think about. And then also like you can think of this like as like 1 over 1, 1 over 1, 1 over 1. It's like you see a pattern, right? It's like a bunch of odd numbers down here, 1 always up here, and it's always going, it's oscillating plus minus plus minus. Apparently all this is pi over 4 if you do it until the end of time. And then if you multiply that by 4, that result, you get pi. Like that is one way to calculate pi. And so we in computer land are working with floats that only have 16 digits of precision. Let's just go up to like this guy, 1 over 9999. 9,999, because that would make it easy on us, right? We don't have infinite precision anyway, so let's just stop there. That's a nice small number. That'll be pretty close to pi, yeah? So let's generate some sequences and do math on them with NumPy operations and try to compute an approximate value of pi. That will be fun. So let's try that. Does the idea make sense? That's what I want. And so I would like to pick out, I think what the easiest way and the way that your book recommends is let's pick out the positive terms like plus this, plus this, plus this, right? Plus this, all the way down there. Those are the positive terms. That's 1 over 1 plus 1 over 5 plus 1 over 9. And you see the pattern here is now it's going up by 4s because it's every other 2, right? Every other odd number. So it's plus 1 over 11, all the way that way. So that's like our positive terms. And then our negative terms are these guys. I can use a different color maybe. Boop. That's like minus 1/3, minus 1/7, minus 1/11. And so we could generate that number as well separately. That's one way to do it. Like take 1/3, give me 1/7. So like add them at the start. Still up by 4 every time, right? 1/9, all the way down to this. We'll get there. And then if we just take all that and we put a negative sign out in front, then we'll get the negative version of all that, yeah? So if I take those guys, that thing, plus that thing, just only going up to 1 over 9,999, we will get a very good approximation of pi. That'll be great, all right? So that's the game plan. I want to show that to you. And now, let's make it happen. So I'm going to do the positive ones, and I'm going to ask you to try to build this one, all right? So while I'm doing it, try to think about how would you use np.arange to build, you don't have to put the negative sign out, but these numbers somehow, right? I guess I want the denominators first, because that would work, right? If I generated 1, 5, 9, 11 all the way to like 9, 9, 9, 9, 9, it would work out, right? That would be the positive denominators. Then I also want 3, 7, 9 onto that. So think about your one as I do mine. But if I do this, np.arange, if the last one is negative, then the positive terms, the very last one that we're adding is plus 1 over 9997, right? For positive ones. So we want to go up to that. So I want to go from 1 to 99998, I guess, so we don't hit 9999 by 4s. Do you see how this will give me the thing at the bottom of all of the fractions I care about for our positive terms? Positive terms. And this is our negative terms. Now I want to generate the sequence 3, 7, 9 all the way to, because I want the 999 this time. So think about it. np.arange something, something, something. I want you to stare at it for a little bit. This is how we learn. So how can I build what I want for the negative terms? Can I get the bottom parts here, those denominators for the negative terms? What can I give to arange? Can you think about it for a minute? Discuss. I want those negative terms denominators, all right? I'm just working on the denominators right now. We'll eventually turn them into fractions. But now I want 3, 7, 9 all the way to 9999. How can I get that? Exactly that. Try it out. Does it make sense what I want though? So we're going to need that. So the bottom part of all the things what we're going to start subtracting. We got the bottom part of all the stuff we're going to add. Let's see add. Question?
Yeah. I just want to ask like why it is the same exact thing, just like so why did it give me like nothing from anything? Oh, never mind.
There's fewer things.
Yeah, I don't know. It's because of
Yeah, I looked at the size and like, can I print this out to you in one screen? If we wanted to start with 3, that kind of gives away the very first thing we need to get, right? The very first denominator is 3. We can't get 1 at the beginning. So the first thing should be 3 here. And then we want it to go up to, like the very last negative term is 1 over 9999. So I need it to go up to here. What does that mean I should give for the ending point? Something bigger, right? Yeah, because it's only if I give this, it will not go up to it. It will miss it. Oops. And then it's still by 4s. So you see how it's going to miss it if I give this. So if I give it 1 more, 10,000, now it really will go up to 999. Does that make sense? So those are our positive and negative denominators. And then we're going to do some cool math. So this is pos denoms. We'll save that away as a variable this time. And this will be neg denoms. Question?
So whenever we're like trying to calculate like where we want it to end,
Mhm.
or we want it to end,
Mhm.
could we use a float number, or would that not work? Does it need to be by integers?
No, it should be fine.
Like 9999.5.
Yeah, that shouldn't be the end of the world. But then it's going to start saving everything as floats.
Oh,
That's the only difference. There shouldn't be any precision loss for us, though. And so let me have them printed out, too. Oops, so there's that one that we made, and then neg denoms, that one that we made. And now we can do cool stuff, because you saw that I did this, right, before. It was like I was able to multiply the temps f by 2, and it like took everything in that sequence and it multiplied everything by 2. You can do the same with division. So like to build, because what I want is like not the sequence 1, 5, 9. I want like 1 over 1 plus 1 over 5 and 1 over 9. So I can take 1 and divide it by pos denoms. Does that make sense? That's going to work. It'll go into every piece and like 1 over that thing, 1 over that thing, 1 over that thing. It'll look a little weird. But I promise it's making 1 over 1. There it is. 1 over 5, which is 0.2. Saving it as scientific notation. You know what the E means now. 2 times 10 to the negative 1. And the next one is 1 over 9, which is a repeating fraction in decimal land at least. And it's going all the way up to that. Does that make sense what's happening there? So that's 1 over all those things as a sequence now. 1 over 1, 1 over 5, 1 over 9. They're all together, which is cool. So that's those. And so those are like the positive terms now. 1 over pos denoms. And then the same for the negative ones. The negative terms is 1 over the negative denoms. And that will give me 1 over 3, 1 over 7, 1 over 9, because I built this. 1 over 3, 1 over 7, 1 over 11, excuse me. And that will work. Okay, so I'm getting all of those denominators. They're still positive, though. I haven't introduced the negative sign. If you look at the neg terms, they're still positive. There's nothing there yet. But I think that's what I wanted to say. So we looked at pos terms as well. That one is correctly already positive. And so now all I need is to take, right, all the positive terms and add them to all the negative terms, having put a negative sign out in front of those negative terms. So another way to do it is like all the positive terms minus the negative terms as well. That would work. So either way you want to do it, that will be our answer. So I'll take, you want to sum all these up, and sum all these up. The way that you can do that one way is a sum function. What is the sum of all the positive terms? Positive terms. Plus, or sorry, it's going to be minus the sum of all the negative terms. Minus the sum of all the negative terms. So that'll sum of everything in the first sequence, minus the sum of everything in the second sequence. And that's the answer. And that's supposed to be an approximation for pi over 4. So you take another 4 there. And in theory, if you do all that, gotta use parentheses because of order of operations. That is accurate-ish, right? To how many decimal places? 3.5. Good enough. So that's kind of cool. You do it up to 1,000 or 10,000 terms, and or at least 1 over 10,000-ish, and you get about 3 decimal places of precision out of the deal. So you have to do a little bit more work to get a better approximation for pi, but that's kind of cool that you can use sequences pretty readily to compute something. And so that's our first taste of that. Are there any questions about what we just did in this example? We have a use of sequences. It's pretty cool. Let's see what else. Yeah, I think I'll just show you some cool stuff with tables. That's the last thing. I think we can finish these slides today. So if you take a column of a table, you get it back as an array. So let's remember tables for a second. We'll have a whole chapter on those soon, so don't worry. But tables live in the data science library, which we've already imported, which is good. And to read a table, I want to read our Pokemon table. You're welcome to go to our code from class and drag them in if you'd like. But here's our Pokemon table. It's got a bunch of data, and the names of the Pokemon are way over on the side, because why not? So there they all are. And we've got a bunch of data about all of the Pokemon, like what is their number, what is their speed, what is their type, their main type is type 1, their secondary type is type 2, all that fun stuff. So yeah, let's include that file by saying make it a table, table.read_table, that file name, and it lives in my data folder, at least for me. It always depends on where you're doing it. So like this notebook file is out here, and then the data folder is inside of that, and it has Pokemon.csv inside of it, just like that. So that'll give me my table, and I'll call it Pokemon, and we can print it out just like the default first 10 column or first 10 row like showing of it. That's what gets printed out to you. So yeah, here's my Pokemon table. It's called Pokemon. Whee! And then you'll want to go back and remember all the kinds of table stuff that you can do. We'll get very acquainted with it, but I just want to say this last bullet. If you ask for a column of a table, and you can do that, dot column. These are like table operations, so you might want to stare at this one day, because we're going to get through all of these eventually. But one thing that you can do to a table is ask it for just give me one column, please. And so let's get just the names of the Pokemon. You remember that there's a select, right? Where's the names? There they are, the names column. So you can say Pokemon dot select, and then you can give the name, and that will produce a table with just that column. If you want the column itself as like an array, because that's what it's really stored as secretly, they're all working together. The data science library and the NumPy library, you can ask for Pokemon.column and give the name of the column. We want the name column, the column named column. Oops, and I can't spell Pokemon today. Boop. And so here now it will give me back now that column as an entire array. And I can do array stuff, like convert them all to all caps or something. I don't know. I can get all this. Okay? So you can say dot column on a table to give you back that column as an array. And you can do all the fun array stuff with it. Get the differences, get all that fun stuff. So let's see. Yeah, let me just show you like one interesting idea. You can get the in this table, there's special attack, generation. What else do we have? It's hard to show. There's just a bunch of numbers. I guess what in my example that I want to give like where is it? There's defense, and then there's also attack. That's like what you usually care the most about for your Pokemon. Like what is their base attack stat? So let's get just the attack column for every Pokemon. Every Pokemon ever. And so that's going to be Pokemon.column attack. Attack. And so that's a big long array of numbers, and you can save that. So this is like attacks. You can save it somewhere, and then you can do math on it. I guess I'll print it out so we can have it still. But there was, I don't know, You can ask for the sum of all the attacks. Now you can do all that fun numbery stuff. You can ask for the average, like what's the average attack of any Pokemon ever? Remember that one? It was all up here. It's like dot mean. That's one way to do it. You can ask the array for its average. Attacks dot mean. That's that. But there's other ways to get the mean too. There's like so many different synonyms in Python for that. There's like a numpy function that's built in, like np dot, what's it called? There's np dot mean attacks. It's another way to do it. There's also np dot average attacks. Like no matter how you want to say it, it's usually there. That's kind of interesting. There's 3 different ways to do the exact same thing. There's even more if you want to think about it this way. Like what's the sum of all the attacks divided by the length of the attacks, right? Because that's the underlying way to calculate the average, right? Give me the sum of everything divided by the size, how many things there are. So yeah, you can get a piece of your table out and you can do array stuff with it and analyze it with all of the different ways that you know how to poke arrays. Any questions about any of that? Just a bunch of ideas, a bunch of stuff that you need to see in order to do your work. It is a little all over the place though. So definitely come back to this. Look at these words. At least you've seen them once now. That's the important thing. Yeah. I think if we're good, that's pretty much that chapter. So there's just two short chapters for today. Random stuff that you need to know from this chapter for your lab. I have another miscellaneous section with just one thing. Boop. I would like to teach you how to combine arrays and strs in a weird way. So again, if you want to ever output something in an array, you may want to like separate stuff. Like one, if you've got an array, let's say of numbers that you've already turned into strs, let's say. So here's an array of string-like things. They could just be words if you wanted them to be words. There's a way to like spit all these out really quickly to generate one string out of the entire array. Because if you were to say str, convert it to a string, it looks a little odd. All right. There's a way to make it a little bit prettier. So if you've got an array of strs, all right, and you'd like to like separate it with like a comma, like make a CSV file, for example. That's what we're reading in. You can say, give your separator as a str, and you say dot join, and then you give it a sequence. So it's a weird little combination of things. What that will do is it will take each piece of that sequence and join it all together with whatever you gave there. So it's going to say 1 plus comma space plus 2 plus comma space to join between that and the next one. Isn't that weird? So that's something you can do. This sequence, though, on the right, the thing that you're giving as you're joining it, the sequence, sadly has to be strs. So I have to, one day, maybe I'll show you how to like take an array of numbers and you'll have to convert them all to strs in order to do this. So you can do it like this and be like, and, I guess that would work. Oops. 1 and 2 and 3. That's one way to do it. So yeah, you can combine, you can join together every piece of your array as long as they're all a bunch of text with that original string. So that's an operation technically on strs. Cool to think about. All right. So yeah, I just wanted to show you that. Now that you've seen it, it will make sense when you see it again in a future lab because it will be there. All right. Yeah, I think that's all that I wanted to say about sequences. Do they make enough sense to us? Just a bunch of numbers, a bunch of anything all at once in one place. You can get at each piece if you need to, and then you can combine them in cool ways. All right? Yeah, I think that's all that I wanted to say for the day. All of the next things, like just for fun, right? We announced and released, this is us, right? We released all of the homeworks and labs. You're welcome to start on the next ones once you finish the current ones that have due dates. But the next ones that have due dates, like homework 2 and lab 2, it's going to be chapter 6. That's what That's the knowledge we require to do those. So I won't be given any new due dates today. All right. But yeah, any last questions before I stop the recording? All right, that's all I got.